In Chapter 4, we're going to look at rational functions in their graphs. The content in the lecture material for 4.1 and 4.2 are kind of combined into one section here because it doesn't really kind of make sense to break it apart. So we're going to be covering both 4.1 and 4.2 in this lecture. A rational function is a quotient of two polynomials. So much in the way, if you think of the traditional name for fractions, those are referred to as rational numbers, which was the quotient of two integers. Well, a rational function is going to be the quotient of two polynomials. So we have f of x, which is equal to some polynomial up in the numerator, we call it p of x, divided by some polynomial in the denominator, which we call q of x. The domain of a rational function is going to be the set of all x's such that the denominator is not equal to 0. One of the things that we remember about polynomials in and of themselves is that the domain of any polynomial is all real numbers. So for any value of x you get, you can always plug it into p of x and get out a value. We can always plug it into q of x and get a value. And as long as we're able to perform the division, then that will produce a value for f of x. The only restriction we have, once again, is we cannot divide by 0. So to find the domain of a rational function, simply take the denominator, set it equal to 0, and those would be the values of x that will not be in the domain. For example, if we look at example A here, if we want to find the domain of f, all I'm going to do is take the denominator, set it equal to 0. We would subtract 7 from both sides, and we would find that the value x equals to -7 would give us a division by 0. So the domain of the function f is going to be all values of x except -7. Recall that properly speaking, we should be putting this in interval notation. This is the set from -infinity up to, but not including -7, and then union -7 to +infinity. Let's do the same thing for part B. Let's see if we can find the domain of g. We're going to take the denominator, set it equal to 0. With this one, you can either factor it or use the perfect square property. I'll use the perfect square property. I'm going to add 9 to both sides. I'm going to then go ahead and take a square root. Remember, when you take a square root of both sides, when you do that number part of it, you have to have the plus and the minus. So we get two values here. They're going to be plus and minus 3. So those are the values that would give us a division by 0. So the domain of g is going to be all values of x except -3 and +3. So x cannot be plus or -3. In interval notation, that's going to look like -infinity up to, but not including -3. Then from -3 to +3, and then union 3 to infinity. So this would be the domain of the function g. In order to investigate some of the properties of rational functions, let's begin with what's perhaps the most basic rational function, which is the reciprocal function. The function f of x equals to 1 over x simply takes whatever your input is and is going to do 1 over it. We can very quickly look at it and analyze it and see that the denominator is going to be all x's except 0. So we can't have a 0 on the bottom. And then what we can do is if we look at the graph of it, let's try to figure out what's happening near that disallowed value 0. So remember, we're not allowed to plug 0 into the function, but one of the things that we can do is plug in anything else that's different from 0. So if you look at this table, what we've done is we've created kind of a sequence of values here coming in from the left-hand side. So if you look at where 0 is on the number line, 0 would be right here. And if you're to the left of it, those would be negative values. What we're doing is we're taking a sequence of negative values that are getting closer and closer and closer to 0, just to see what's happened to the outputs of the function. If we plug in -1, we would get out -1. If we plug in -0.5, we would get out -2. If we plug in -0.1, we would get out -10. And you can kind of see the pattern here. What's happening is, as we're plugging in values that are getting closer and closer and closer to 0, the outputs that we are getting larger and larger and larger negatively. And what that's showing us is that the graph here of this function is approaching negative infinity. So here's our graph. The closer we get to 0, the further and further and further down the graph is going to go. We can represent this fact using a limit approach type notation. We would say that as x approaches 0, and now we use a subscript here. This subscript, this little negative sign, does not mean a negative number. It means the left-hand approach. So if you think of a number line, right? If we had the number 0 in general, we know that the negative numbers would lie to the left of 0, and the positive numbers would lie to the right. Or you can think of it as like decreasing or increasing here. So if we're approaching x, if x is approaching 0 with this symbol here, that means that we're approaching it from values that are on the left-hand side. What's happening to the outputs in our function values is we said that they were approaching negative infinity. Okay. So that's this new notation. As x approaches 0 from the left, f of x is approaching negative infinity. We can do something similar and to see what happens if we look at the right-hand approach as x approaches to 0. So now we're going to pick a sequence of values. They're going to get closer and closer to 0 coming in from the right-hand side. So I could start with 1, then 0.5, then 0.1, 0.01, 0.001, and we see that these values are all getting smaller as I get closer to 0. If we look at the corresponding outputs, what's happening to the outputs? Well, if we plug in 1, we get out 1. If we plug in 0.5, we get out 2. Plug in 0.1, we get out 10. We see that these function values are getting larger and larger and larger, and they're going to approach positive infinity. And when we look at the graph, that's exactly what happens. When we approach 0 coming in from the right-hand side, the function values get higher and higher and higher and are approaching positive infinity. Using the notation, we can say this. As x approaches 0, now we're going to use a plus superscript. Again, that doesn't mean positive or negative, it means directionally. As we approach 0 from the right, we see that the function values themselves are approaching positive infinity. So as x approaches 0 from the right, f of x approaches infinity. We can now look at and try to investigate the end behavior of this function. We've already studied in the previous chapter, we talked about end behavior of a polynomial, and that's kind of trying to determine what happens to the values of the polynomial as x increases without bound, either positively or negatively. So here we're trying to figure out what's going to happen as the x values increase, what happens to our f of x values. So here we can pick some increasing values of x that are positive. So let's look at the end behavior over here to the right. Notice that if we plug in 1, we get out 1. If we plug in 10, we get out a tenth. If we plug in 100, we get out a hundredth, 0.01. But in particular, what's happening is these values are getting smaller and smaller and smaller, and they're approaching 0. We would observe something very similar if we tried to approach negative infinity for x. So when x gets larger without bound, if we look at what's happening to our function values, they're getting smaller and smaller and smaller, and they're approaching 0 through negative values. So that's going to look like this. Again, we can represent this and write this in limit notation. For example, for this part, we would say that as x approaches infinity, the f of x values are approaching 0. And over here, we would say that as x approaches negative infinity, once again, we see that f of x is also approaching 0. When we put all of this information together, we get a very accurate graph of the reciprocal function, which is 1 over x. Notice that the domain of this function, we knew that x was not allowed to be equal to 0. So we had x So putting it all together, we see the graph of 1 over x. And one of the things that we want to kind of highlight here is that we know that the domain of this function was x cannot be equal to 0. And if you look at the graph, what we see at 0 is an object we're going to define. This is what's called a vertical asymptote. And the reason why it's a vertical asymptote is it's a value of x that as the function values, as x approaches that particular value 0, the function values approach either negative infinity or positive infinity. So just to kind of recap the notation we've seen, this is what we're going to call our arrow or approach notation. When you see this being written, x approaches a from the right, this means that the x values are approaching a from the right. So if you can think of like a number line, like if we had our horizontal axis, that's where the x-axis is. Somewhere you would have this number a, and if you're approaching it from the right-hand direction, meaning coming in, getting closer from values that are slightly bigger than a, that would be the right-hand approach. If we approach a instead from the left, getting values that are sequentially getting closer and closer and closer to a, but they're smaller than a, this would be the left-hand approach. And then these I think we're already kind of familiar with. X approaches positive infinity, x approaches negative infinity. Another basic rational function is the graph of 1 over x squared. It has the same domain as the previous function. Again, we can't have the denominator be equal to 0. To solve this, we can take the square root of both sides, and we see that there's going to be one restricted value, and that value is x cannot be equal to 0. We can make a table of values if we need to, but what you would find is that as we approach 0 coming in from the left-hand side, we see that the function values approach positive infinity. We can summarize it like this. If we approach 0 coming in from the right-hand side, we once again see that the function values are approaching positive infinity. Using the approach notation, we can write it like this. If we also want to talk about the end behavior, let's see what's happening as x approaches positive infinity. As x approaches positive infinity, we see that the graph is going down and down and down. It's approaching 0. So we would say that as x approaches positive infinity, f of x values are approaching 0. And similarly on the other side, if we let x approach negative infinity, looking at what happens really far out here to the left, we once again see that the graph is going down and down and down, and it's approaching 0. So as x approaches negative infinity, we would say that f of x approaches 0. One of the key features of these rational functions is the presence of what's called vertical asymptotes. We say that the line x equals to a is a vertical asymptote of the graph of a function f if f of x increases or decreases without bound as x approaches to a. So for example, for this graph here, the first graph on the left, we would say that x equals to a would be a vertical asymptote for this graph, because as we approach a coming in from the right-hand side, we see that the function is approaching positive infinity. Again, a is the asymptote here. As we approach a coming in from the left, the function values are approaching positive infinity. As we approach a from the right over here, the function values are approaching negative infinity. And for this last graph, if we approach a from the left, we once again see that the function values are approaching negative infinity. So if a function approaches an infinity, as x approaches a set value a, then that value x equals to a is referred to as a vertical asymptote for the function. For our discussion in this class, we will almost always exclusively work with rational functions that are in simplified form. And what that will present to us is the idea that whenever you want to look for a vertical asymptote, those will be the places where the denominator is equal to 0. So how do we find these vertical asymptotes? This is very important. Let's suppose we have a rational function f is p over q, where p and q are both polynomials. And we also have to make this added assumption too. This is very important. We want for p and q to have no factors in common, meaning whatever p of x would factor into and whatever q of x would factor into, they can't have any common factors. If they do, then it's possible that we might not have asymptotes. You might actually get something called like a hole in the graph. But for our class, we're always going to assume this, or at least you can check and make sure this is true. But if this is the case, if they have no common factors, then those same values we were locating when we were finding the domain, the zeros of the denominator, those will be the ones that produce our vertical asymptotes. Let's take a look at example 2. Here we have f of x equals x divided by x squared minus 9. To find the vertical asymptotes, let's take that denominator, set it equal to 0. You can solve this one by factoring or using this perfect square root property. And we would get two solutions, x equals plus or minus 3. So the graph in A, just a quick check though, we need to make sure that these two values aren't also going to be factors of the numerator, which would mean that they would have to be like zeros of the numerator. And that is true if you plug either 3 or negative 3 into the numerator. It's not going to make that top also equal to 0. So the two vertical asymptotes for the function f would be x equals to negative 3 and x equals to positive 3. So be a little bit careful for g of x. For g of x, if we go ahead and set that denominator equal to 0, we have x squared minus 4 equals to 0. You could also use the square root property on this one, but let me just factor it instead. So I'm going to treat it like a difference of squares. It factors as x minus 2 times x plus 2. We can now go ahead, set each factor equal to 0 independently, and we get x equals to 2 and x equals to negative 2. Okay. Of these, only the x equals to 2 is going to be a vertical asymptote. The question is, well, what then happens with x equals to negative 2? Notice that if you plug negative 2 into the numerator, so if I plug the 2 in, notice that 2 plus 2 would be equal to 4. So this value here makes the bottom 0, but it also doesn't simultaneously make the numerator equal to 0. So this one is a vertical asymptote. If you plug negative 2 into the numerator, however, that also gives us a 0 up top. And what's happening here is if we go back to the original function g of x, if the numerator is completely factored, which it is, it's x plus 2. If we totally factor that denominator, we have x minus 2 times x plus 2. What happens is the numerator and denominator share a common factor. Those x plus 2's kind of cancel each other out, and so it would equivalently reduce to 1 divided by x minus 2 for all values of x except that negative 2 one that we kind of canceled out. Because of that cancellation, what that means is that we have a hole here. So if you were to actually zoom in and look at the graph of g of x, there's not going to be an asymptote at negative 2. Rather, what we would have would be a hole in the graph. Okay. So be very careful here. To find the vertical asymptotes, it's not just simply the numbers that make the denominator equal to 0. You also need to make sure that those same values of x do not also make the numerator equal to 0. If they do, then that means that both numerator and denominator share a common factor. And if that factor is able to end up canceling, only the zeros of the denominator in the reduced form of the rational function end up being vertical asymptotes. Anything else that would have canceled out in terms of a factor and a 0, those would represent holes in the graph of the function. So we get one vertical asymptote for g. For h of x, we're going to do the same thing. Let's solve where the denominator is equal to 0. Using the square root property, you would have negative 36 over there. x equals plus or minus the square root of negative 36, which is an imaginary value, okay? Plus or minus 6i. Because those are not real numbers, they're not going to appear on the graph, so we would see that h of x has no vertical asymptotes. Okay, there are no real values that would make the denominator of h equal to 0. The next thing we're going to investigate is horizontal asymptotes of rational functions, and these are related to the end behavior of the function. We say that the line y equals to b is a horizontal asymptote for the graph of f if f of x approaches b as x increases or decreases without bound. So for example here, if we look what happens as x approaches positive infinity, we see that the function values are getting closer and closer and closer to this height of this y value of b. So we would say that as x approaches infinity, the function values are approaching b, and we would say that the line y equals to b is a horizontal asymptote for the graph of f. Similarly, we have the same thing here. As x is approaching positive infinity, we see that the function values are decreasing, they're going down and approaching that height, that value y equals to b. Here's another one. As x approaches positive infinity, we see that the values are getting closer and closer to b, so y equals to b would also be a horizontal asymptote for this graph f. One of the things that's nice is that we can actually classify and locate the horizontal asymptotes by simply comparing the highest powers of x in both numerator and denominator of your rational function. So if you look at the leading term of the numerator here, this is going to be the nth power. So we have a to the n, x to the n, and the leading term in the denominator is going to be b to the m, x to the m. To determine whether or not or what type of horizontal asymptote we have, what we need to do is compare the degrees of those leading terms. For example, if n is less than m, meaning if the power up top is smaller than the power in the bottom, so if the largest power is in the denominator, then it will always be the case that y equals to 0 is the horizontal asymptote. So if the highest power of x is in the denominator, it's always y equals to 0. If they share the same highest power, so if the highest power in the numerator is the same as the highest power in the denominator, then in that case, the horizontal asymptote is simply going to be the ratio of their leading coefficients. So you take the coefficient of the highest term up top, the coefficient of the highest term on the bottom, and that ratio, an over bm, will be our horizontal asymptote in that case. And then lastly, what happens if n is bigger than m? Well, if n is bigger than m, that simply means that the highest power would be in the numerator. If the highest power is in the numerator, then there is no horizontal asymptote. We'll investigate this third case a little bit in more detail in the case that the top is of degree 1 higher. But in general, if the numerator has a higher exponent, there is no horizontal asymptote. Let's take a look at example 3. They ask us to find the horizontal asymptote for each rational function. So we need to compare the highest powers up top and the highest power on the bottom. Here we see that the highest power of x, which is the x squared term, lies in the denominator. And that means that we're going to have a horizontal asymptote of y equals to 0. And a lot of times you'll see me just abbreviate it. I'll just abbreviate horizontal asymptotes HA. Let's take a look at part B. Same thing too, you need to begin by identifying the highest power in the numerator and the highest power in the denominator. For g of x, notice that they both have the same highest power. That means that the asymptote is going to be the ratio of their leading coefficients. The leading coefficient up top is 6. The leading coefficient on the bottom is 3. So it's going to be 6 over 3, which is 2. So our horizontal asymptote for g would be y equals to 2. If we look at c, the highest power in the numerator is x cubed. The highest power in the denominator is x squared. But overall, the highest power of this rational function lies in the numerator, and that means that there will be no horizontal asymptote. We can graph some pretty basic rational functions by using our transformation information. So the graphs of 1 over x and 1 over x squared, we covered those briefly above. Those are two graphs that you want to add to your parent list of functions. So if you remember back from a previous chapter, whenever we did transformations, there were certain key graphs that we wanted to memorize. Things like absolute value, x to the n, for even and odd. We also talked about graphs of things like square root of x, cube root of x, etc. Here's two brand new graphs you want to memorize. Everybody should know what the graph of 1 over x looks like, which is this graph here, as well as the graph of 1 over x squared, which would be this graph here. If we know what those new parent functions graphs look like, then we can graph some transformations of those by using our information from that transformation section. For example, if we look at the graph of g of x, we see that we have an x minus 2. So we're subtracting 2 on the inside. We recall that that should be a horizontal shift. So that's going to be a horizontal shift 2 to the right. We also have addition by 1 on the outside of a function. That should be a vertical shift up by 1. The next thing you will want to do whenever you're graphing these is first translate and move the asymptotes. So for the parent graph of 1 over x squared, remember the original asymptote for that, the horizontal asymptote was y equals to 0. If we shift a horizontal line 2 to the right, that wouldn't change it at all. So the shifting of the horizontal line, 2 to the right, won't move it at all, but then we need to shift the graph up 1. So the new horizontal asymptote for this graph is going to occur at y equals to 1. Let's now shift the vertical asymptote. The vertical asymptote for 1 over x squared was originally at x equals to 0. We need to first shift it 2 to the right. So 2 to the right would move it to here. And then from there, if we wanted to shift it up 1, shifting a vertical line up 1 is not going to change the line at all. So we get this. And then from there, as long as you kind of know the parent graph, you can kind of go ahead and plug this in. The shape should look like this. Like this. And just to be a little bit picky, it looks like my line's kind of coming up. Let me tweak that just a little bit. Remember, as we approach negative infinity, it should be getting closer and closer and closer to the asymptote. So this is the graph of g of x, which was obtained by knowing the parent graph for f, along with some of our transformations. In general, if we wanted to talk about a strategy for graphing rational functions, it's going to begin by finding a lot of the key things that we've done in the past. For any graph, we would like to know things like the y-intercepts, the x-intercepts. We know that asymptotes are now a key feature of our rational functions, so we want to identify any vertical and horizontal asymptotes. If you want to look for symmetry, symmetry can also be helpful. We know how to check for y-axis symmetry and also origin symmetry. And then if needed, if we need to find additional points, we may need to do that. But let's see if we can put this all together and graph our first rational function by hand. Let's go ahead and graph example 5. Let's begin by finding the vertical asymptotes and horizontal asymptotes for this function. To find the vertical asymptotes, we're going to set the denominator equal to 0. We have x minus 1 equals to 0. Add 1 to both sides, and we get x equals to 1. Now that's only a potential vertical asymptote. Before we go ahead and claim that it is, you also need to make sure that it doesn't also make the numerator equal to to 0. Certainly, if you plug 1 in, that would give us 2 times 1 minus 1, which is going to be equal to 1. So it makes the denominator 0, but not simultaneously the numerator. So that means that this definitely is going to be a vertical asymptote for our function. The next thing we want to do is look for the horizontal asymptote. Remember, this is done by comparing the highest power of x in both numerator and denominator. The highest power of x in the numerator is x to the first. The highest power of x in the denominator is also x to the first. So because they have the same highest power, that means that the horizontal asymptote is going to be the ratio of those leading coefficients. So it's going to be the equation y equals to 2. So we do have a horizontal asymptote. The next thing we're going to do is look for the x-intercepts and the y-intercepts. For the x-intercepts, remember this is where you set f of x equal to 0 and solve. That is, where is 2x minus 1 divided by x minus 1 equal to 0. This is a rational equation. You can multiply both sides by the denominator, and we get 2x minus 1 equals to 0. If you go back to the notes, whenever we talk about finding the x-intercepts, a fraction is only ever 0 wherever the numerator is equal to 0. So if you wanted to save a little bit of time here, you can simply just set the numerator of this equal to 0 to find the x-intercepts. So just kind of a quick recap here. When you have a rational function, setting the denominator equal to 0 finds you your candidates for your vertical asymptotes. Setting the numerator equal to 0 finds candidates for your x-intercepts. We can add 1 and then divide by 2 to both sides, and we get x equals 1/2. So we have an x-intercept. It's the point 1/2 comma 0. Remember, to find a y-intercept, you need to evaluate f of 0. So we're going to plug 0 into the function. We would get 2 hold on one second. So if we plug in 0, we are going to get 2 times 0 minus 1 divided by 0 minus 1. This is going to be negative 1 divided by negative 1, which is positive 1. So our y-intercept is going to be 0, comma 1. And with just that information, we should have quite a bit that we need to graph this thing. Let's begin by graphing the vertical asymptotes. So we have a vertical asymptote x equals to 1. Remember, technically an asymptote is not a portion of the function's graph, but it's a line that the graph will approach. So here's our vertical asymptote at x equals to 1. We have a horizontal asymptote. If you look back through it, is y equals to 2. So y equals to 2. I'm drawing my horizontal asymptote. So we first plot our asymptotes. Now let's go ahead and plot any of the points or intercepts that we found. We have an x-intercept at 1/2 comma 0, which would be right here. We also have a y-intercept at 0, comma 1, which would be right here. And now let's go ahead and draw as much of it as we can. Over here, we know that the graph has to follow this horizontal asymptote. It has to pass through these 2 points, and then it has to follow the vertical asymptote. So that gives us this portion of the graph, which is right here. Unfortunately, we don't have any points over here to the right of x equals to 1. So there's 2 possibilities for what the graph might look like. It could either look like this, because we know it has to follow the asymptotes. That would be option 1. Or the second option is that maybe it would come down and look something like this. Okay? And this is where in the notes they talk about trying to find some other points to kind of help us out a little bit. Okay? So if you're not sure what's going to happen here, we could pick another value of x that's over here to the right. Let's plug in x equals to 2. If you plug 2 into the function f of 2 is equal to 2 times 2 minus 1 divided by 2 minus 1. That's going to be 4 minus 1 over 1, which is 3. So this graph would also contain the ordered pair 2, 3. We plug in 2, we get out 3, and that would be the point right here. And then because we know that the graph has to follow the asymptotes, it's going to have to be like this. So on occasion, if you don't know where a graph is in between or on one side of an asymptote, you might need to do something like this to plot some additional points. Logically, though, you can also do this without plotting any additional points. And the way that you could do that is as follows. We said that there was two possibilities. It either has to follow like this, or the only other possibility is it could follow and be below. The reason why this wouldn't work, so if you try this as a potential candidate, the reason why that wouldn't work is that in order to follow both of those asymptotes, at some point in time, that graph would have to cross the x-axis. However, if you go back to our x-intercepts, the only x-intercept for this graph we solved for is going to be at 1/2, 0, which means that a situation like the bottom case here would be impossible because we can't create or find any other additional x-intercepts. So just by process of elimination, this wouldn't work, and that would tell you that the other portion of the graph would have to be this part, which is above. Let's do another one of these. In example 6, we want to graph f of x equals 3x squared divided by x squared minus 4. We'll once again begin by finding the vertical asymptotes. We're going to set the denominator equal to 0. I'll factor it this time. It's a difference of squares. X minus 2 times x plus 2. Set each factor equal to 0. Solve each of those resulting linear equations. We get x equals to positive 2 and x equals to negative 2. Before we go ahead and claim either of these as vertical asymptotes, you would need to make sure that neither one of them also makes the numerator equal to 0. And that's clearly going to be the case on this one. You can either plug 2 or negative 2 into the top, and it's not also going to make the numerator equal to 0. So we do get two vertical asymptotes, negative 2 and positive 2. For the horizontal asymptote, we're comparing highest powers of x in both numerator and denominator. Once again, the top and bottom have the same highest power. That means that the horizontal asymptote is going to be the ratio of those leading coefficients. That's going to be 3 over 1, which is 3. So we have a horizontal asymptote y equals to 3. The next thing we'll look for is our x-intercepts. Technically, this comes from setting the function equal to 0 and solving, which in this case is equivalent to setting the numerator equal to 0. To solve 3x squared equals to 0, divide both sides by 3. We get x squared equals to 0. You can simply take the square root of both sides. Plus or minus 0 is just one value. That's going to be 0. So we have an x-intercept of 0, 0. For the y-intercept, we need to evaluate f of 0. If we plug 0 into the function, this is going to be 3 times 0 squared divided by 0 squared minus 4, which is 0 divided by negative 4, which is also 0. Okay. So our y-intercept is also the point 0, 0. Let's go ahead and try to graph this. If you wanted to go for symmetry, by the way, I didn't do it for the last one. Notice that this graph was neither symmetric with respect to the origin or the y-axis. If you check for this graph, though, this one actually will have symmetry. If you look at f of negative x, this is equal to 3 times negative x squared divided by the negative of x squared minus 4, which is the same thing as 3x squared divided by x squared minus 4, which was our original function. So that tells us that this is an even function, and then the implication of that is it's going to have y-axis symmetry. And that can be very useful in kind of paring down and cutting out some of the work we need to do. Let's try to graph this then. So first things first, let's begin with doing our asymptotes. We have a vertical asymptote at -2. And also +2. We have a y-intercept of 3. Like this. And then we have a y-intercept, 1 point, our x-intercept and y-intercept both happen to be 0. In terms of drawing this, we know it has to follow the intercepts, like this. But we don't know what's going to happen over here to the left of -2, nor do we know what's going to happen to the right of +2. So this is the case where you might want to go ahead and do some additional points. For example, if I try to evaluate f of 3, let's plug 3 into the function. F of 3 is equal to 3 times 3 squared divided by 3 squared minus 4. That's going to be 27 over 3 squared is 9 minus 4 is 5. So we get 27 over 5, which is about 5.4. It's about 5.4. So if you're looking for another another point in the graph, we would have 3 comma 5.4. And because we have that y-axis symmetry, it would also be the case that if you plug in -3, we would also get 5.4 out. So over here at 3, I'm going to go up 5 and not quite a half, like right there. And that kind of tells us what the rest of this graph is going to look like. Again, we could have also figured this out because to the right of 2, you have 2 choices. Either it's going to look like this, or because it needs to follow the asymptote, it would look like this. But again, you can rule this out because we know that the graph is not going to cross the x-axis at any point other than 0, 0. So this would be impossible, and that would kind of lead you to the fact that it has to look like this. And then from symmetry, if it's up here, it'd have to be symmetric on the other side of the y-axis. So putting it all together, this is our graph of 3x squared divided by x squared minus 4. The last thing we're going to look at is what's called a slant asymptote. So we know that whenever we're in the situation where the degree of the numerator is higher than the degree of the denominator, then we get no horizontal asymptote. Whenever the degree of the numerator is exactly 1 more than the degree of the denominator, we instead get an object which is called a slant asymptote. Okay? To find the slant asymptote, what we can do is actually perform polynomial division. So let's take x minus 1 and divide it into x squared plus 1. Okay. So I'm going to do this with the old school division. Remember, x squared plus 1, it has no x term. So make sure you have a 0x whenever you do this. X goes into x squared x times. We then multiply that x by our divisor, like this. We need to subtract to go down. To do that subtraction, change it to addition of the opposite. We get x, bring the plus 1 down. X goes into x once, so I have a plus 1 here. This is going to give us an x minus 1. Again, we need to subtract this. To do that subtraction, change it to addition of the opposite. And what we get is going to be 2. So when we do this division, what we find out is that f of x is equal to, here's our quotient, it's x plus 1 plus remainder over divisor. When you're looking for the slant asymptote, the equation of the slant asymptote is y equals the quotient. So you can ignore the remainder part. It's whatever you get for the quotient, like this. And the reason why that's the case is when you're looking for the slant asymptote, this is going to be a line that the graph is going to approach at the infinities. Well, when x gets really large, so when x increases without bound, essentially what's going to happen is this fraction here is going to get smaller and smaller and smaller and smaller. So this fraction is going to become almost negligible and will approach 0 as x increases without bound. Meaning x is going to approach either positive infinity or negative infinity. And what that means is that for large x, our function f of x is going to behave and look very closely, resemble the graph of x plus 1, and that's the equation of our slant asymptote. Okay? So again, to find equations of slant asymptotes, this occurs specifically when the degree of the numerator is exactly 1 higher than the degree of the denominator. You do polynomial division, and whatever you get for the quotient, you can forget about the remainder part, just what you get for the quotient without remainder, y equals that is the equation of our slant asymptote. Let's take a look at example 7. They ask us to find the slant asymptote for this function. Notice that it is going to have one because if you look at the numerator, it has the power of x squared. Highest power of the denominator is x to the first. And we're exactly in the case where the power of the numerator is exactly 1 larger than the power of the denominator. So we're going to do polynomial division. And notice for this one, you can do that, which is what you have to do in general. If you're clever about it, if you like that synthetic division, we are dividing by x minus 3, which is something you could use synthetic division on. Okay, but I'm just going to do it with the long division. X goes into x squared x times. We then take the x, multiply it by our divisor. We need to subtract. To subtract, let's change it to addition of the opposite. Negative 4x, the x squareds cancel. Negative 4x plus 3x will give us a negative x. The negative 5 comes straight down. X goes into negative x, negative 1 time. Going to go ahead and subtract. To do that, we're going to change it to addition of the opposite. And we would get a remainder here of negative 8. So if we're looking for the equation of our slant asymptote, it's going to be y equals this. Y equals x minus 1. Let's take a look at example 8. Let's actually graph this function. F of x equals x squared plus x minus 6 divided by x minus 3. To start, let's begin like we've been doing. Let's first find the vertical asymptotes. We set the denominator equal to 0. Solve, we get x equals to 3. Let's be careful here. Let's make sure that that value does not also make the numerator 0. So if I plug 3 into the top, that's going to be 9 plus 3 minus 6, which itself is going to be equal to 6. So that makes the denominator 0, but not also simultaneously the numerator. So we do have a vertical asymptote of x equals to 3. The next thing would be to look for the horizontal asymptote. And we're in that case where the highest power is in the numerator. So there is no horizontal asymptote. Okay. However, because the top is exactly of degree 1 higher, we will have a slant asymptote this time. To find the slant asymptote, I'll let you all do the work on this one. I'm just going to do it with the synthetic division. If I were to do synthetic division, which we're able to because our divisor is x minus 3, it would look like this. 1 comes down, bottom times block, add to go down, bottom times block, we get 12, add to go down, we get 6. This would be our remainder. But what we would have after that would be x plus 4. So the quotient is x plus 4, and therefore the equation y equals x plus 4 is going to be that of our slant asymptote. And again, this is as opposed to having to do the long division where you do x minus 3 into x squared plus x minus 6. If your denominator is not of the form x minus c, then we would be forced to, and we would require doing the long polynomial division. Let's now find some intercepts here. For the x-intercepts, we set f of x equal to 0, which is equivalent to setting the numerator equal to 0. We get x squared plus x minus 6 equals to 0. This factors as x plus 3 times x minus 2 equals to 0. Set each factor equal to 0. And we get x equals negative 3, x equals positive 2. So our intercepts are negative 3 comma 0 and 2 comma 0. To find the y-intercept, we need to evaluate f of 0. This is going to be equal to 0 squared plus 0 minus 6, all divided by 0 minus 3, which is negative 6 over negative 3, which is positive 2. So we have a y-intercept of 0 comma 2. Having some points and some asymptotes, we should be able to graph this thing. You can check for symmetries, by the way. There's no symmetry on this one. It's not going to be symmetric with either the y-axis nor the origin. So let's start with our vertical asymptotes first. We have a vertical asymptote at x equals to 3. That's like this. And now we have our slant asymptote, which is of the form mx plus b. It's a straight line that has a y-intercept of 4 and a slope of 1. So run 1, rise 1, run 1, rise 1. But this would be your slant asymptote, like this. Let's now plot our points. We have the intercept at negative 3, 0. We have 2, 0. And we also have a y-intercept of 0, 2. Like this. We know that the graph has to follow the asymptote, so it's going to follow this slanted line as we approach infinity, has to curve, and it has to follow this vertical asymptote like this. So we have part of the graph. We know what the graph looks like to the left of the asymptote x equals to 3, but we don't quite yet know what's going to look like to the right of 3. This is where you might want to do a couple of things. You can either plot another point, or you can kind of think about the different possibilities here. We know the graph has to follow the asymptote, so there's two choices. Either it's going to follow the asymptotes like this and kind of be above, or the other choice would be to do something like this, where it would have to follow the asymptotes below like that. Again, you can rule this out because that would create the presence of another x-intercept that's not there. So you can ignore that. The graph that's in blue would be our graph of our rational function with a slant asymptote.